Here, okay? So this is what, the 9th review session, so next one will be the last one. Okay? We'll get over it. So, who wants to try the first one? The first problem. Okay? I'll bring the iPad back. So it's asking for, you see, mechanism, right? So that would be the arrow pushing, as well as the products, right? As well as the products, all right?
I don't know the
See,
mechanism.
try it. I'm going to grab an apple while you start, okay?
Right.
So in general, you see you can change color here. So if maybe start with black for the structures.
Right.
And then here you can like switch, like this, you want to do red, right? For the arrows, that would be awesome. Okay?
Thank you.
And maybe you can comment a little bit if you want. There's people watching the recording.
All right.
I'll be back in a second. I'm just going to grab it.
Do you want to comment on this?
I have no comments.
So what are we starting with? First step.
X.
That is the product.
First
That is
step.
correct.
Okay. Do you want to try it?
Now the hardest part is the
mechanism?
mechanism. That's the Markovnikov
okay.
problem. So what is
So this has to become a cation.
Yeah.
The plus.
All right.
Yeah.
So this is plus. And
No,
then,
you have to draw the arrows.
I don't know.
Draw
Let's
the
see.
arrows.
So here's an apple.
Thank you. Yeah, this is as far as I got.
No, let's do it together, okay?
Okay.
How about we do it together?
All right.
Is that
You
okay?
got this.
Yeah.
So the product is absolutely correct, right?
Yes.
So you started putting a positive charge there. What you never want to do when you draw a mechanism is don't change the starting material.
Okay.
Okay, you see, you changed the starting material. You don't want to change that. Okay, so we take that positive charge off. So what you want to do is, what's the first? So the HX, right? That's an acid. So one good thing to do is put the HX there again, like this. Okay, and now what does the acid do? It protonates the double bond, right?
All right.
So do you want to try that?
I still don't.
You don't want to do it?
Yeah,
Okay,
Michael,
that's
you
fine,
got
that's fine.
this.
Do you want to try?
I got this.
Okay,
Oh yeah.
I'll get you another apple so you can
Oh,
continue.
yeah.
All right?
I think this is an easy one. No, no, it's
Michael, you
happening.
blew it.
Yes, that's the protonation step. That's similar to what we have in Lex.
Hold on.
Maybe I can bring the whole bag with me.
Apple King.
All right.
Ooh, okay.
Let's see. This is great. Ready mix tertiary carbocation. And now the X minus is the nucleophile. And it attacks. So if you draw the X minus, if you draw one lone pair, I would suggest you draw all
Oh, okay.
four of them, just to be consistent,
Mm-hmm.
Either draw none or all, but so if you are using it as a nucleophile, draw all is
Okay.
better. That's perfect.
Cool.
And then,
But wait, there's more?
no, I think that's it. Just draw the arrow so it points at the product.
Okay. Is this an eraser? Wow.
Yeah.
Look at this.
So that's great. All right.
Wow.
And here's your apples. Thank you so
Yes.
much.
Thank you.
That's great. Okay, thank you guys. Appreciate it. So this is great. So you see, this mechanism is a standard one, right? We just have different electrophiles and different nucleophiles, but it's actually, I think it's almost simpler than chapter 7. It's pretty straightforward. So it's good. So why don't we go to the next one? So today might not be a super long review session, actually. Okay, let me go back to the previous one. Yeah, so this is probably correct. Okay, so now this one. Who wants to try this one? Oh, let's see. We'll go with you, okay? Let me get an apple so I don't have to walk forward and backward. Okay, here we go.
I have something different.
All right.
Great.
Good. Okay, that's
Yeah.
certainly one of the products.
Okay.
All right. So now, what
Should I draw
other
them?
products could form? So draw the mechanism for this one, right?
Okay.
To start. And then there might be other products because you see it has an S there.
I think
I was just looking at it. I thought otherwise it's exactly the same as the previous round. So there must be something special about it. Good. You forgot one methyl group in the intermediate. Right?
Oh, wait.
See the one pointing straight down?
Yeah.
Perfect. One more lone pair. One more lone pair.
Oh.
Right? Because Br minus
Yeah.
is like an octet. Okay? But otherwise, this is great. So now the question is, what else could form? Right? If you want to keep trying, or we can ask somebody else.
Is it
There's.
useful?
Let me think. You are actually right.
Okay.
So you're right. So you want to draw those. So you see, tell me your name. Amanda just drew this product, which is perfectly correct. And you see the way Amanda drew it is without stereochemistry, right? Mm-hmm. So, yes, right? Because even the starting material actually has a chiral center here already. Okay, see that? And I'm just, by not drawing in stereochemistry, it means it's a 50-50 mixture of both stereoisomers, right? It's a racemic mixture. And then the product, you see, forms another stereocenter here. So technically it forms as two enantiomers, right? So you could draw it like this, for instance, plus the other enantiomer. The best thing is to just draw it without stereochemistry. And, but now there's another product, another regioisomeric product, which can come from a rearrangement. In this case, you see, the carbocation down there can rearrange. Because you see, it's a secondary carbocation. So how can it rearrange? What do you guys think? A hydride shift. Okay. So maybe you can draw it. Okay. Maybe just like on the right, it is another alternative product. Okay. So actually for the mechanism, the best way to do it
Shit, Lily.
before you continue is maybe draw it without, just from the common intermediate.
Okay.
Right? Because it forms the same type of intermediate. Okay, and then so it's easier to see, don't draw it, the intermediate again. It's like just branch off from that intermediate. Yes, so it does a hydride shift. Why does it do a hydride shift? Because you go from a secondary to a tertiary carbocation that way, right? And there we go. And you get that. Then I get the other product, right? Perfect. And now this doesn't have a chiral center, right? Thank you so much. Okay. All I'm going to do is make the arrow point a little bit more at this one. Okay. All right. Any questions? So keep the rearrangements in mind, right? For these kind of reactions. And then again, the rearrangements only happen with these kind of reactions where you go through carbocations. If you go through the mercuration, demercuration step, right? We discussed this morning. Then you don't get rearrangements. Okay. So let's go to the next one. Here we go. Yeah. You want to try? Okay, and then you can do the next one if you want. It might be a hard one, but up to you. Yes, you draw your plus.
Actually, Lily, I need to go back. You do red by again. I need to change the color.
Proton transfer. Is this the exact same one we had in lecture? To me, they all look very same. But you see, it's always the same. It's always the same mechanism. It's actually that's not too bad. It's just a lot of steps, but if you know how to draw it, it's really. You see by now, because you have seen these steps as well, I think SN1 reactions will look easy to you again, right? Because they don't, see, it's all connected, okay? So it's becoming easier, I think. The water deprotonates it.
Oh, sorry, hold on. How do I go back?
You need to attack the hydrogen, right?
Eraser.
Take off the hydrogen.
Can I push this to go back?
Yeah, yeah. Oh, perfect. Yes, right? Always attack the hydrogen when you do deprotonation. Okay? Done. Perfect. You see the H3O plus comes back out again because it's the catalyst, it's not consumed. Right, here would be the apple. Thank you. Okay. So that's problem one. Yes, Isaac.
For the industry, we write the H3O plus at the end.
The question is, do you have to write the H3O plus at the end? Can't hurt.
Okay.
I think I will not, for these kind of questions where I'm asking for the major products, that I usually mean the organic product,
Okay.
right? So the complex molecule. So as long as you draw that, unless I'm specifically asking for like things like H3O plus. If you draw it, I mean, we will not take off any points if you draw it, for sure, right? It's, yeah, okay. Generally, you just draw the organic product,
Okay.
that's fine. All right, so let's look at the next one. So now we want the synthesis of this product from an alkene. So, yeah, who wants to try? Okay, I'll get that too.
This is local along straight line.
Yeah. This looks
Okay.
pretty good. This looks pretty good. So, yeah. Then that's this mechanism. So, there are different ways now, right? There's three possible different starting materials you could use. So can you draw all three of them?
Yeah. I'll try.
Right, so this mechanism. You can finish up the mechanism.
okay.
We'll write it once more. Can't really hurt.
So here's one.
So that's one of them, right? Then the other one, yeah, this one, where the double bond is the 6-membered ring. What about another one? Yes. So which one do you think is the best? I mean, usually the one which is the most readily available, okay? And what you will see generally in the future is something which is more symmetric is often easier to synthesize and more available, like it's cheaper to buy. 'Cause it's more available. So the last one you drew, I think, might be the best. 'Cause
This
it's
one?
just, it's more symmetric, you know?
This one
Yeah.
right here.
That's probably would be the first choice. You can, but you generally, what people do is they go, you can search like databases and see which one is available, right? Here we go. Thank you. Okay. So what I'm saying is, when you do these kind of synthetic problems, okay, you see you can make it from a double bond. You try to come up with all possible solutions, right? And then you try to figure out which one is the best. So don't just stop with the first one which comes to mind. Okay. Think about whether you can come up with all of different ones and then pick the best one out of there. Okay. In general, because here this is still pretty simple. It's just a one-step synthesis. But once you do like multiple steps, right? At the end of chapter 8, we'll know a bunch of reactions. So then you can actually make these in a more fancy way. I'm just trying to see if you have learned the reaction where you can. Yeah, no, that's what we can do. Okay. Let's go to the next one. Oh, okay. So basically, this is a combined problem, right? Where you first you need to take the name, draw a structure out of it, and then figure out what the product is, and then just circle the one. Who wants to give that a try? 4-methyl-pent-1-ene, and then 2 enantiomers form, right? Because it adds. Oh, okay. Let's. Who wants? You guys are both raising your hand. Maybe you can do the next one if you. Is that okay? Yeah. Here we go. All right. So if you draw the whole thing out, explain a little bit, the mechanism. And again, today will not be super long review session. I think that's fine. If you guys have any questions, we can discuss that now. If you have questions about the answer stuff. We're almost done here.
I know.
So, well, how many more problems do you want to
6.
Oh, so we're like halfway done. Yeah. This is still fairly easy because we just started chapter 8.
Do you
right?
want
So
me to
yeah.
draw the front and back side attack or no?
No, you don't have to. Yeah,
Okay.
you could just. So if you circle the. Oh, you wrote which ones form, right? Yeah. Okay. Yeah, this is great.
Okay.
This is great. I think this is great.
I'll draw
Thank you.
another one just in case
Yeah,
you
yeah.
want it.
Thank you. Let's get you this.
Nice trade.
Yeah. So in general, okay. You see the way you draw the front backside attack. This is good, but I would rather we leave it like that.
Okay.
So if you draw 2 arrows, you know what I mean. Otherwise, it will get confusing, unless you draw them in different colors or so, right? That's why I did it in different colors in lecture. So be careful whenever you draw arrow pushing. Only do it like kind of like one step at a time, right? Okay, but this is great. So I'll circle these 2 guys. Okay, let's go to the next one. Do you guys have any questions? Again, it's just front backside attack, kind of like we talked about in lecture. These guys. Oh, okay. So this is just methyl shift. Which ones? You see, it's actually a good problem. It's like, because we see a lot of rearrangements, right? The question is, when does a methyl shift happen? When do you have a hydride shift and these kind of things? So what do you guys think? Who wants to try that one? Do you want to give that one a try, or
I don't really.
you don't have to? It's a totally different one. I understand. Anybody else want to? Number 4.
No, she's answering the question. Like which one?
Oh, you are answering the question. That's a good question. Let's see. What about 1? What about 3? Okay, so 3, no, right? 3, there's nothing next door where you can make a more stable carbocation, so you can rule out 3. Now number 2, yes, you can do like this, right? The methyl shift. Okay, and that will give you a tertiary carbocation. Now what about number 1? Can somebody draw a methyl shift for 1, which gives you a nice tertiary carbocation? What about this? So you go from a primary to a tertiary carbocation, no? Or, to me, that looks like a pretty good methyl shift. Right? Because you do this, let me draw the product. then it goes like this. Right? And here we are going to get, so I'm going to eat an apple myself because I figured, maybe not. I only eat chocolate now, I bet. All right. See, that's what happens, right? So I think both 1 and 2 can undergo methyl shifts. And 1 is probably even more preferable to do it because you're going from a primary to a tertiary carbocation, right? There's a huge driving force there. Okay? So that was good. Any questions? So again, just practice looking at these methyl shifts and, the hydride shifts so that you really see all the situations, right? So we could go to number 5. Okay, who wants to try this? Major product, right? Formable reaction HCl with 3-methyl-1-butene. Okay, give it a try.
Okay. Oop. Uh-oh.
Just thinking about some.
You got it, yeah.
Well, sorry. How do I erase?
Let me see. 3-methyl-1-butene.
I don't remember how to erase.
Oh, how to
That's
go
right.
back?
Or how to erase.
Oh, yeah.
Yeah.
Okay. And then. And would it do a shift?
Yes.
Yeah. Okay.
This is a hydride shift now, right?
Okay.
So that's why the problem is there. See, so if you do a methyl, otherwise it would be too easy, right? So if you do a methyl shift here, then you still get a secondary carbocation. But if you do a hydride shift, then you get a tertiary carbocation.
Mm-hmm.
So that's why we do the hydride shift now, right? Done.
Okay. Not done. Not
What's the
even
name of this?
Oh, okay. Butane is the base. And then 2 chloro 2 methyl. Is that right?
That's right.
All right.
And so do you form, is this stuff chiral? Do you form the R or the S product?
No. It's a
Or it's
chiral.
achiral. Okay. Because there's
Yeah.
2 methyl groups.
So,
All right.
yeah.
Perfect. Thank you.
Awesome.
Any questions? Let's move on. I have an idea. I will give you some synthesis problem after, okay? So these are a little bit old, these apples. It's all I've left. Okay, what's this one? This is same again, or is this different one? Sorry, it's like I'm just trying to see if sometimes there might be even that these all look so similar to me, so I can't distinguish whether we already did it or not. Who wants to do this one? Major product of the following reaction. So this is a little bit different. You haven't seen this reaction, okay? Isaac, you can try it.
My
Yeah.
guess, when I looked at it.
But you see, that's the nice thing about this problem. It is similar to what we saw before, but you haven't seen this particular reaction, right?
Yeah.
Because it's not a hydration reaction, right? We're not adding water. What are we adding? We're adding methanol, okay? But now water is very similar to methanol, so if you think about the mechanism, what might happen, right? Instead of you adding OH, you're adding OMe.
Yeah.
Okay? So you can guess and draw the mechanism of how it happens, even though you've never seen the reaction before, right? That's Try.
So the mechanism would be.
Oh, yes. Oh, yes. Yes, Isaac. So
Yeah.
where does the H... Well, first of all, what happens with H2SO4 in methanol?
I don't know.
So it's a solvent leveling effect.
Okay.
So methanol here would probably be the solvent.
Yeah.
So there's a lot of methanol around. Methanol will pick up. What happens? Think about what happens with water or H2SO4 in water. But the H2SO4 is a very strong acid, like pKa, like -7 or something. The sulfuric acid. So it will give away all of its protons to water.
Mhm.
So it will make HSO4 instead of H2SO4. It will make HSO4 minus, right?
Mhm.
The conjugate base of sulfuric acid, and then it will form H3O plus. Okay. So essentially, what is in there is no longer methanol and H2SO4 now. It's MEOH2 plus.
Okay.
Right? The equivalent compound would be H3O plus in water. So maybe we draw that. Okay. Because
Okay.
you see, so there's two correct ways I think of doing this. One is you can, but the one you drew is not.
Not right.
Not completely, because your cation was right, just where the
Okay.
H plus comes from, okay? Because you took the H from the methanol, and the methanol is not acidic enough to protonate the double bond. It's kind of like we cannot take the H from the water to protonate the double bond, right? Somebody asked the question in the morning. So what we want to do is take it either from the H2SO4, or even better is take it from this one. So you would have the methanol, which is protonated, right? That's what forms. So let's actually draw the whole thing, okay? The absolute whole thing. So we have the time. So we will do, see what happens is you have methanol, which first gets protonated by H2SO4, right? Yeah, bless you. So this is H2SO4, okay? And so now the methanol is taking away a proton from here, okay? And so then it's forming, I'm just running out of space here. So then it's forming MEOH plus, all right? And now, this thing is what protonates the double bond, because that's a strong acid. Similar pKa to H3O plus. All right? And so now we can continue. Now you can continue.
Okay.
Right? Now you can continue. But that's important. So whenever you draw things like these mechanisms, think about which are really the active species. Like what's the acid, right? Sometimes there are multiple H's in there which could act as the acid, but pick the most acidic one. Okay, or if it's a basic mechanism, pick the most basic, site to do the deprotonation. All right. And again, never use an acid, for example, in a mechanism where you have a strong base present, or vice versa. Okay. Yes.
If you assume that the protonation happens with like when it gets to MEOH adding to it and you have to deprotonate it, can you use HSO4 minus?
Yes, you can use HSO4 minus.
Okay.
That's fine. It's probably better to use methanol because it's probably a better. Yeah, but you could use HSO4 minus.
Okay.
Yeah, that's fine.
How do you erase? What do you?
Pick this one, number 18.
Okay.
Yes.
And then back to the one.
Uh-huh.
And then.
Okay.
Go.
The last thing is just you deprotonate.
Yeah, you get rid of the H, and so you get that one that I circled, number 1, by. What would deprotonate it? Another MEOH?
Another MEOH,
Okay.
or the H
Or that
SO4
HSO4 minus?
Yeah.
Okay.
Okay.
pick one.
Yeah, pick one.
I guess technically it'd be the sulfur, right?
No, it would
It'd
be
be
the
the
oxygen.
oxygen.
It would be the oxygen.
So
Okay.
it's kind of hard to see it.
Yeah, it's a
but
little bit hard to see,
sorry.
but that's fine. The other thing is when you do this, for example, when you start from the methanol, when you start the arrow on the methanol, right? Remember to drawing the lone pairs, right?
Okay.
Because you want to start the arrow on the electron pair.
Okay.
So it's always good to draw in the lone pairs, the one, at least for the atoms where you are
Yeah.
starting the arrow from. Okay. So any questions about these? If not, let's do another one together. Maybe look, we have another couple minutes. You know, we can do one. So, for example, can you guys come up with a synthesis of, let's see, something like this. Maybe that's too long. Hold on. Let's make it a little bit smaller, otherwise it's going to go forever. Yeah, this one. This one. See if you can you come up with a synthesis. That's a real compound. It's very useful. How would you make it? With like things like SN2 reactions and things like that. So we can do it together, okay? We can do it together. Who wants to start? So there's different ways. First, you start to think about how you can break some bonds, okay? And which bonds we can form. The more keep things symmetric, that usually helps. So let me get you started. So which bonds can we form carbon-carbon bonds easily with the reactions you have learned? No. What kind of reactions have we learned? What bonds we can form? Carbon-oxygen bonds, right? How can you form a carbon-oxygen bond? What kind of reaction have we learned which can form carbon-oxygen bonds? Like SN2 reactions, right? So if you take like an alcohol, you make it O-, that can attack, for example, an alkyl bromide, okay? And kick out the bromide, then you would get an oxygen-carbon bond, right? So where do we have oxygen-carbon bonds? Which we can break, a lot of them, right? For instance, you know, we have oxygen-carbon bonds here, 2 of them, see? So if you break both of them at the same time, that will simplify your molecule, then that will break it up, okay? But then, so that's one option, right? Then there is another option, for instance. How about these 2 bonds? Have you learned a reaction to make these yellow bonds? These yellow carbon-oxygen bonds? No. Because you can't, if you wanted to make the yellow ones, right? You would have to do something like this, where you put the alkyl bromide here. Does that make sense? Plus, so that would be the yellow ones, right? Plus OH, or O-. And then this part. Oops, sorry. But you see what I mean? So these 2, you would keep the oxygen on that part. Now what's the problem with this? With this connection? The problem is you cannot do an SN2 reaction on a structure like this where you have double bonds. You can never do that, because you need, for an SN2 reaction, it's the way we learned it, you need to have a primary or secondary normal alkyl halide, not a double bond on there, okay? So there are reactions, special reactions, where you can actually do this kind of thing, but you haven't learned about them, so you can't really use them yet, okay? So this is not the way we want to do it. But the other way around actually is good. So we're not going to go with this yellow disconnection. We're going to go with the other one. So you can go with the red way. So let's take off the yellow ones. Okay. Take off this guy. So the red ones is good. The red disconnections are great. So can somebody draw me the starting materials we need to do this red disconnection? You guys are not a huge fan of the synthesis stuff yet. So that's good. We need to practice. You'll get the hang of it after a while. It's good we are doing this. So who wants to try the... You can try it. Alkyl halide plus an oxygen, right? O minus.
Like have the
Try it.
alkyl, okay.
So this is just going to be OH?
Yeah,
OH,
so
right?
you have this ring.
Mm-hmm. Yes.
Plus, and then you just
The
throw
the bromide there, right?
do I have to draw it all, this whole thing?
Draw it, yeah. It's good. You need to get, the other thing you guys have to get used to, okay? Particularly for 142, like the spring is you need to get used to quickly draw like really complex structures relatively quickly, okay? This is not super complicated. Like this is still a pretty simple molecule. Like in the future you might have to draw larger stuff, okay? So start to get used to that. Start to get used to it. Okay, this is pretty good. This is pretty good, and that's why I'm saying get used to drawing it. See, what you did is you lost some carbon atoms.
Yeah.
Let me show you, okay? That's why it's good exercise, okay? Otherwise, this is perfect, right? So let's count. What I recommend, okay? If you draw these structures, count them, okay? So you want this you see, count 1, 2, right? 3, 4. Just count along. 5, 6, 7, 8, 9, 10, 11. Right?
So the bromines should be on 1 and 11.
Yeah, the bromine should be on 1 and 11, right? And you see what you have is now 1, 2, 3, 4, 5, 6, 7, 8, 9.
Yeah.
So you lost 2 carbon atoms. So you need to, you see,
Yeah.
you need to insert 2 carbon atoms back here. You see?
Yeah.
Like this and like this. Now it's correct, right? You can just, and you just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the numbering really helps.
Yeah.
Okay? So always, whenever you draw stuff, double check yourself whether you lost a carbon or you added a carbon, or it's really easy to get lost at the beginning. Just be very, very meticulous about it. All right? So that's good. Now, next. So what are the reaction conditions to get there, to go forward? It would be, you need a base, right? You would add a base, and the base would deprotonate the OH to make O minus, and then it would do an SN2 reaction, right? With 2 primary alkyl halides. So there will be base. So what kind of base can you use?
We could use whatever kind we wanted, right?
Whatever. Yeah, as a sodium hydride, you would add sodium hydride, for instance, to this thing, and then and then that would be step number 1, plus the phenol. With the OH there, that's called the phenol, sorry. And then number 2 would be, you would do like DMF, right, and mix the 2 together. And then, you see, you need to make a ring. How do you make a ring? Intramolecular, yeah, it's like it reacts with itself, right? 2 molecules couple, and then the next one happens intramolecularly. But now the thing is to do it intramolecularly. Ideally, what you want to do in practice, you want to keep it really dilute. If you keep it really dilute, then the chance of it finding another molecule is less, and so it will give you more of the ring. Otherwise, it will start to give you a polymer where everything couples together and like make you a long chain. Okay. Another way to do then this reaction in practice, you add like a metal, like a cation, like sodium, which binds in the middle of all the oxygens, and that helps make the ring. So that's fine. You don't have to know all that stuff, but that's the first step. Now we continue, right? You want to simplify this thing. From what else could it come from? you can keep doing this game. You can keep cutting off bonds. So for example, you can say, all right, this could have come from, you can cut these.
Oh, further up the chain?
Yeah, you keep doing the synthesis. It's a multi-step synthesis, right? The end goal is usually to take a molecule and break it down into something much simpler. Does it make sense? So this could have come from, for example, something like this, where you take the upper part here, this part, and this part. Right? So it gets simpler and simpler. You see? So now you can say this could come from OH. Sorry, let's draw it a different way. So OH, oxygen, and then OH here, right? Okay, plus 2 equivalents of this so-called dibromoethane. Okay, you guys see that? That couples onto there. I see you guys are nodding your head. Or not nodding, shaking your head. So let me show you how it happens, okay? Can I go to the next slide? I'll draw it forward so I can actually draw it. So here's what happens. I'll draw you to make it a step forward, okay? So it's going to be OH, oxygen, OH. Okay, that's what you're starting with. Then you're adding a base like sodium hydride, or let's say T-butoxide, right, or something like that. Potassium T-butoxide. And you're adding 2 equivalents. Right, because we have 2 hydrogens we want to deprotonate. Okay, so here the arrow needs to be longer, sorry. Now, this will take off this proton, right? And we are getting, and this happens twice. Okay, so what we are getting is this thing. Does that make sense? So we just deprotonate the whole thing. And now we are adding this dibromoethane. And now we can do an SN2 reaction. Sorry, that's a little bit ugly. Right, like this. Then we're getting to this one. So this is not the perfect synthesis. So that the other one comes in, the next one. Because you can do it all in one step. Generally what you would use in this case is you would add excess of the dibromoethane so that it will mostly do this reaction twice rather than cyclizing intramolecularly, right? And then you get to your product. Here we go, okay? See that? That's what I was thinking. And then you could simplify it even more, all right?
And that's in order to make the second, or just that other precursor?
That's to make the second precursor, yeah. And then you take the second precursor and make the final product, right? You see how we are doing this? We basically start to cut, you take the final molecule, and then you start to look for reactions, easy reactions where you can make it, ideally making multiple bonds at the same time, so it simplifies it more and more. And then you do it step by step, right? You get to the precursor, and then you find the reactions which can make the precursor. And then, this is still pretty simple because it's always the same reaction. But now we know more reactions, right? So you could do like addition reactions to make this guy. And then, so for example, this one then could come from, you could say come from this, right? But another option, I'll go back here, another option for this precursor, this one, you could say, okay, this could maybe come from an addition reaction, right? Where you have something like, something like this. Right? And then you're doing like some sort of HBr, but that wouldn't actually work because it would put the bromine on the other carbon. right? This wouldn't work. So if you do HBr, you would put the bromine over here, because that's a more stable carbocation. So that's then a bad idea, right? So we wouldn't want to do that. You see what I mean? So you have to look at different ways to do this, okay? All right? I think that it's still helpful to go over this so you get some feel. We'll do more of this synthesis stuff in lecture. Yes? One question. Yeah.
My initial way I thought of doing this was different.
Uh-huh.
I don't know if it would work at all, but would it be possible to do like an E2 thing with starting with this and like this is a base, or is that just too weird?
The question is, yeah, can you do an E2 reaction, for example, to make the benzene so potentially yes, you could eliminate to make the benzene ring, but generally here's for synthesis. Generally, if you see an aromatic ring, those are usually readily available materials. You learn. So generally, you leave those there. So, for example, you will once you do more and more, of these synthesis problems, you will know what's available, what's kind of commonly available, what's not so much available. That's very much experience. But aromatic rings are very stable, and so they are actually good things to keep. That usually you can buy those materials, right? So. But it's an option. There's ways you can do eliminations to make aromatic rings. Okay? Okay, thank you guys. So we will do more stuff on Friday. Just keep practicing. I also to upload the sapling. Okay?